So for V, we can observe that. For U, we can observe this. That from going from 1 to 2, if alpha is such that, for example, this point, assume, is delta V and T divided by AV. And this point is delta U and T divided by AU. So if you go this, so you see you want to reduce the probability. For example, alpha is here, and it cuts that. So you want to reduce this probability, and it is bounded by beta. What is beta? Beta is just for any vertex U and V, you can define as the maximum of this distance, maximum of delta V and T divided by AV minus delta U and T divided by AU. I mean, such that delta U and T divided by AU is less than 2 for any terminal T. So if shaded area is big, if this shaded area is big, then we are unlucky. We want to reduce the probability that they are being cut. So we are unlucky. We make this big fault, this big error. And what is this big error? This amount C of U and V, D of F of U and F of V. Because we have lots of 1 here. Now we have lots of 1 here. So we get a bad problem. If you round it, then we get this big, and we are unlucky if this shaded area is big. So beta is an upper bound on the size of the interval in which alpha can lie in order for V to be assigned to T, terminal T, but not U. So the interval in which alpha can lie in order for V to be assigned to T, but not U, Kalinski proved that this probability that U and V are separated is less than beta log K. I'm creating some kind of poster, some kind of images to show you the beauty and the proof of CKR algorithm in a kind of animation, because it's really beautiful, and the proof can be understood very easily if you understand that. So they proved that Kalinski, one of the authors of CKR, C stands for Kalinski, proved that this probability is upper bound by beta log K. So to make tight zero extension, so it is enough. It suffices beta to be very small. So imagine this: you have U, you have V, so it should be cut, okay? So it should be at least in that direction of you have some terminals here. And so any of them, so there are many layers because you have the distance, you have got your distance, which are fractional. For example, 0.3456. Another one, 0.16. So you have to round it. And the CKR, if you go to CKR algorithm, as I said, the mother gets and supports until later terminals in that permutation. So permutation shows that which one is going to be mother that protects U and V from being cut by others. And so if you say that this is cluster, let's say this is cluster I, And this is cluster I minus 1. This is cluster I plus 1. I minus 1, I cluster. So this interval is very important. And so you can see something like, for example, U and V are here, and you go until you reach some terminals, and then terminals are like this. They double each time. So doubling, we double it to reduce the probability of edge being cut. And the number of terminals doubles at each successive radius. So we want to reduce beta. So around each of the clusters, there is an interval of width at most beta, which if alpha were chosen in that interval, you could be assigned to a different vertex. But they will only be assigned to different terminals if in addition one of the terminals in that cluster is chosen before any of the other terms. So the permutation matters. So everything is related to that permutation. So let's consider the worst case. As I said, you have U, you have V, you have AU, and you have 2AU. And this is a layer that we call it cluster I. And then around this cluster I, you have other, so permutation shows which comes first, which can be the mother, the parent of that, and protect it from being cut. I love this parent notion that Ravi said. By the way, our Ravi is a very good teacher, Indian teacher and professor in, I think, Carnegie Mellon. Yes, I think it was Carnegie Mellon, CMU. And he teaches very interestingly. That's why you never forget the algorithm. So check r.ravi. And he's a very creative person. I really like him. So the cluster I is there, the cluster I minus 1 and I plus 1 is here. So your beta, so this is the width. It should be less than beta. It's bounded by beta. And so delta U and T is less than alpha AU. This means that according to CKR algorithm, U is assigned to T. And if delta V and T is less than alpha AV, so it means V is assigned to T. So whoever comes first in the permutation protects and becomes the parent, protects the UV from being cut. So the tightest case is we pack all terminals between UA and UV, and so so we can say that, let's say, what happens in cluster 0? In cluster 0, you have I equal to 1. In cluster 1, you have 2 to the 1, so it is 2. In cluster 2, you have 2 to the 2, which is 4, which is greater than 1 plus 2. To cluster 3, you have 2 to the 3, which is 8, which is greater than 1 plus 2 plus 4, which is 7. In case 4, you have 2 to the 4, which is 16, which is greater than 1 plus 2 plus 4 plus 8, which is 15. So you see, if you sum all of the terminals, because it doubles, in the previous, all of the terminals from the previous layers, and then you compare it to the current layer, this current layer, it is always the same thing. What I mean is that since the size of the cluster I, this cluster, is about the same as the size of the previous clusters put together, the probability of picking one of the terminals in cluster I before one in a previous cluster is about half, since we double terminals in the next cluster. So the probability of U and V sent to different terminals, in other words, being cut, it is equal to the sum over all clusters. How many clusters? Log K clusters. The sum over beta over 2. Because for any of them, the probability is P times half. Because it is bounded by beta, and it is half because, as I described, because the probability of picking one of the terminals is just we sum over all of the clusters. So we have how many clusters? We have log K clusters. So this becomes omega beta log K, because we have log K clusters of this type. This is the amount that can be layered. How many layers? Let's say how many layers? We have log K layers, because in the next layer, in the next layer, the number of terminals are going to be doubled. So this is the tightest case if we consider the tightest case, then we are done, because nothing can go more than the tightest case. But the authors, Tolver, they improved the algorithm of CKR to log K by this algorithm. They call it algo 2. And they pick gamma like before. The only change is that now a prime V is a minimum of 2 to the S. 2 to the S is greater than 2AV over gamma. And what else? Instead of alpha being between 1 and 2, it is now between 2 to the I minus 1 and 2 to the I. And then this algorithm makes you de-randomize, use the potential to reduce the approximation factor. And a random permutation sigma as before, and then 2 loops 4. For terminals from 1 to K, and this for each assigned vector, the number of it is up to the number of vertices. And the only difference between CKR algorithm and this improved algorithm is that the distance between U and sigma L is now less than alpha A prime of U instead of A of U. And A prime of U is, we have introduced it here. And then we assign vertex U to terminal sigma L. And it is proof that you get a much better factor, much better approximation. And that was what I wanted to share about these interesting CKR and advanced CKR algorithm. Of course, you can improve it because you have lots of ways you can define that. In fact, even if you create a random algorithm with high probability, your algorithm is going to be better than other algorithms. So what I want to share is the work of Moses Charikar in Stanford. First he was in Princeton, and because he's nice, he went to Stanford and many other workshops to share his interesting work. So also the work of Roy Schwartz, the guy who also worked on the CKR algorithm with Makarichev and others, and Rabani, Makarichev, and they continued to work on, Moses Charikar continued to work on the correlation clustering. But his examples in Simon's Institute is very interesting. And he showed that how we can look at mean ST cut. You should watch his video on Simon's Institute, multi-way cut, multi-cut. Almost many problems can be shown to be a problem, can be formulated as correlation clustering. The origin of correlation clustering is from machine learning, but nowadays you can see it is very interesting. It can be a good primitive for many problems in graph theory. So the classical approach to clustering is that first of all I should review what is correlation clustering. It means that we have some edges. Let me call you. So when I say blue edges, it means that they are positive labels. And when I say negative edges, they are negative labels. And we want to reduce the amount of these bad events, because it is red, but it is in the same cluster, or even these bad events like this. This is a bad event because it is a blue. It is a positive label, but it connects different clusters. It is crossing the clusters. So it is bad. So there are two bad cases. If blue crosses the link, crosses the clusters, or if the red stays in one cluster. So this is another bad edge. So the goal is to do clustering in such a way that reduces the amount of bad edges. Of course, we can accept bad edges, but we want them to be as minimum as possible. For example, now why this is important? Because if you have several terminals, for example, terminal 1, terminal 2, terminal 3, and you want them in different clusters. Okay, so assume that this is an edge. And you want them to be, okay, so how do you separate or partition the edges so that they do not cross as much as possible? For example, you don't want this bad edge, this green bad edge, and for example, you partition that. You don't want this bad edge, which is blue, of course. We don't want these bad edges. So if you minimize those bad edges, in other words, you are doing a multi-way cut, because you are minimizing if some of them, because for example, if you say a natural labeling is that I label them if they are if they connects two terminals, TI to TJ. If connects TI to TJ directly, that should be red. Label negative. So it means we don't want them to be inside your cluster. You don't want that to be here. This is bad. You don't want this. You want to reduce that. So this is the problem of correlation clustering. And the classical approach is the global objective, but Moses Charikar, he wants to see what happens if you have local objectives. I mean, minimizing the maximum number of disagreement for edges incident on a single node. So I should rank nodes based on their importance and connectivity.